In this lesson, we will discuss properties of graphs. Now, the first property we want to discuss is the property of symmetry. Now, there are different types of symmetry, and one type of symmetry is something being symmetric with respect to the y-axis. To be symmetric with respect to the y-axis, we need every point xy that is on the graph to also have the point negative xy on the graph. So what does that mean, or what does that even look like? Well, let's say we had this graph right here. This parabola is symmetric with respect to the y-axis because your y-axis is going to be your axis of symmetry. It's cutting it right down the center. Now this notation down here, what that means is if you pick a point, let's say we pick the point right here, let's call it the point 2, 0. So if that's your point, what we know is that there must be another point on the graph such that the x value is opposite. So instead of positive 2, 0, there must be another point over here, and that point must be negative 2, 0. And that's what we have, right? And that goes for any point. Let's say we pick this point right here. Okay, if that's maybe negative 3 something. Okay, this other point over here that corresponds with it is going to be positive 3 something. All right, so if we can change just the sign of the x value where both the points are on the graph, then we know it's symmetric with respect to the y-axis. Now the same logic is true for something to be symmetric with respect to the x-axis. So to be symmetric with respect to the x-axis, for every point xy that is on the graph, then x negative y must also be on the graph. So an example of this would be this sideways facing parabola. It is symmetric with respect to the x-axis because the x-axis is the line that cuts the parabola in half. And if you pick a random point on this graph, let's say we pick this point right here, and let's call it, I don't know, maybe negative 2, 3. Or sorry, positive 2, 3. Call that positive 2, 3. Then there must be another point on the graph where you change the sign of the y value. So there must be another point at 2, negative 3. And that is the case. There'd be a point down here at the value of 2, negative 3. And that goes for any point. So if you pick a point over here, let's call this point negative 2, negative 1. There must be another point on this graph where you change the y value into a positive 1. So we have negative 2, positive 1. And indeed, we would find that we would have a point of negative 2, 1 on this graph as well. So to be symmetric with respect to the x-axis, okay, that must be true. For any point xy, there must also be a point x negative y on the graph. So if you were given a picture of a graph, you can tell very quickly if it's symmetric with respect to the x or the y-axis. But if you were just given an equation or a function, and you didn't have the graph given to you, we need a way to determine if the function or graph is symmetric with respect to the x-axis or the y-axis. So to do that, we need to understand this concept right here that we showed you, and this concept right here, all right, because that's going to be our test, basically. So to determine if something is symmetric with respect to the y-axis, you have to replace x with negative x. And once you do that, we have to see, is the equation going to stay the same? And then to determine if something is symmetric with respect to the x-axis, you replace y with negative y and see if the equation stays the same. So for example, let's say we had this equation here, where we had y equals the absolute value of x plus 4. If we were trying to determine if it is symmetric with respect to the y-axis, so we're doing this first test, what you do is you replace x with negative x. So right here, instead of absolute value of x, we would have the absolute value of negative x. All right, so the question is, would this equation be the same as the one up here? Well, the answer is yes, because the absolute value of a negative number makes it positive. So we can write this as the absolute value of positive x plus 4. All right, it's going to be the same exact equation that we started with. So because it's the exact same equation, when you plug negative x in place of x, the answer is yes, this would be symmetric with respect to the y-axis. Here is a second example, And for this one, we're going to do the second test. So we're trying to determine if it is symmetric with respect to the x-axis. All right, so if you plug in a negative y in place of y, we need the equation to stay the same. So what happens if you plug in negative y in place of y? So we have negative y squared minus 10. Well, when you do that, a negative number squared makes it a positive, right? So that is the same thing as positive y squared. So we have x equals positive y squared minus 10. That is the exact same equation that we started with up here. So because of that, because plugging in a negative y in place of y does not change the equation, that means it is symmetric with respect to the x-axis. And if it did not equal the same equation, then it would not be symmetric with respect to those axes. Now another type of symmetry is being symmetric with respect to a point. So the definition of this says that a graph is symmetric with respect to a point Q if for each point P on the graph there is a point P prime on the graph such that Q is the midpoint of the line segment P prime. Okay, that's a lot of words, a lot of math notation. So what does that mean? Well, let's say we pick a point. Let's actually use the origin as the point. So if this is our point, we'll call that point Q. Okay, what this says is if we pick a point P, we'll just pick any point P, then there must be a point P prime on the graph such that Q is the midpoint of the line segment P prime. So if you have a point P, then there must be another point down here, okay, P prime, such that Q is the midpoint of that segment. All right, so we're just kind of sketching it by hand. It's not an exact length, but that's the idea, where Q would be the midpoint of that segment P prime. Now, typically, you're not just trying to look at one point P. It's going to be like a picture, something like this maybe. So maybe it's a parabola. All right, so maybe something like that, where any point we pick can be matched up with another point over here, where the origin, or this point, is going to be the midpoint. All right, so that's the idea of this. And now, again, we don't want to just have to look at the picture to determine if it's symmetric with respect to a point. We want to have some sort of a test to determine if it's symmetric. Now, before that, understand that whatever point we pick here, let's say that point was, I don't know, let's call it 2, 5. Then this point P prime, the point that corresponds to it, you change the sign of both x and y. So it's going to be -2, -5. That's going to hold true for any point. If you pick this point here, let's say this was point 17. Then there's another point down here, -1, -7, that corresponds with it. All right, and that's going to be true. So to determine if a graph or a function is symmetric with respect to the origin, what we do is we replace x and y with -x and -y and see is the equation going to stay the same or not. So here's an example. We have x times y equals 9. And the question is this function symmetric with respect to the origin? All right, well, if you plug in a -x in for x and a -y in place of y, what's going to happen? Well, negative times negative is positive, so you have positive xy equals 9. So notice you ended with the same exact equation that you started with. So because that happened, that means yes, it is symmetric with respect to the origin. If that did not happen, if you had something different than what you started with, then it would not be symmetric with respect to the origin. Now, there's some terminology we have with these different types of symmetry. So we have what's called even symmetry and odd symmetry. So a function is considered to be even if it is symmetric with respect to the y-axis. And then a function is determined to be odd if it is symmetric with respect to the origin. And here we see two different pictures illustrating those. And we've already kind of talked about that. We've talked about the symmetry with respect to the y-axis, right? For this first one, this is symmetric with respect to the y-axis because the left and the right side are identical. And then this one, this graph would be considered symmetric with respect to the origin, because if you pick any point, so let's say we pick this point here, there's going to be a point where you switch the x, or change the sign of the x and the y value, and it's going to match up with another point down here on the graph. All right, so this graph would be symmetric with respect to the origin, so we consider that an odd function. So this is just terminology for terms that we've already learned in this lesson. All right, now to determine if something is even or odd, we kind of talked about that already as well. But here's a formal definition of an even function. So in math notation, we can say that f of negative x equals f of x for all x in the domain of f. So the way to interpret that is right in here. See, we can replace the x with negative x. Okay, that's the idea. If we plug an x in or negative x in, it's going to be the same equation back out, which is what we've discussed, right? That's how we can determine if something is symmetric with respect to the y-axis. And then for an odd function, in math notation, our definition is f of negative x equals negative f of x for all x in the domain of f. So this has the idea of, as we mentioned, with being symmetric with respect to the origin, that the x and the y values, you can switch the sign and you can have another point on that graph as well. So here we have negative x, so the opposite of x. Here is a negative f of x. That means we're changing the sign of y. F of x is y. So that's the idea here. We can change the sign of x and change the sign of y, and we're still going to have a point on the graph. So we can use these definitions, though, to determine if a function is even, odd, or neither even or odd. So let's say we had the function f of x equals x cubed minus 3x. So to determine if it's even or odd, okay, we need to basically plug in a negative x in place of x to determine what's going to happen to f of x. So if you replace negative x in place of x cubed, what's going to happen? Or negative x in place of x. So now we have negative x cubed, and then we have minus 3 times negative x. Okay, that's going to give you what? Well, we're going to have negative x cubed, right? Negative to a third power is going to be a negative number. Negative 3 times negative x would be a plus 3x. All right, so what happened? Well, what happened is, if you look at the original function, the signs are now changed, right? The signs are changed. It's a negative x cubed minus 3x. If you pull out a negative, that's the same thing. So what we have here is f of negative x. When you plug a negative x in place of x, what happened is it's going to make it into a negative of the original function. So what this indicates is that we have an odd function. So if that's what happens, if you plug in negative x in and the function is now opposite of what you had initially, that means the function is odd. Let's take a look at another example. Here we have g of x equals 3x squared. So what happens when you plug in negative x in place of x? Well, if you do that, we now have g of negative x equals 3 times negative x squared. Well, negative x squared, negative to a second power makes a positive number. So that's the same thing as positive 3x squared. So plugging a negative x in did not change the original function, which means that this function is going to be even, right? Because g of negative x is equal to g of x. So this would be an even function, which means it's symmetric with respect to the y-axis. What about this function? H of x equals 5x squared minus 2x. Well, to determine if it's even or odd, we replace x with negative x. So we now have h of negative x equals 5 times negative x squared minus 2 times negative x. Well, negative x squared would be a positive number, right? Negative raised to a second power is positive. So that would be a positive 5x squared. And then negative 2 times negative x is positive 2x. So how does this relate to the original function? Well, it's nothing, really. It's not the same, so it can't be even. And it's not the opposite signs, because to be opposite signs, we need a negative 5x and a positive 2x. So it's neither even nor odd because of that. All right, so that's the key. Just plug in a negative x in place of x and see what happens. If the function is opposite from what you started with, then it's going to be odd. If it's the same as what you started with, it's going to be considered even. Now another topic dealing with graphs is different translations. A translation in the math context is a moving or a shifting of a graph. So we can do a vertical translation or we can do a horizontal translation. So a vertical translation is determined by adding a number to the function. So if you add a number to a function, that's going to shift the function up that number of spaces. If it has a negative number, so like minus something, that's going to shift the function down that number of spaces. All right, so here, for example, if this is our function f of x, and we were to take f of x plus 3, that would shift the graph up 3. If we had f of x minus 4, it would shift the graph down 4 units. All right, we see that graphed right here. So there's vertical translations. We also have horizontal translations. So a horizontal translation is determined by a number in parentheses. So instead of f of x, we now have f of x minus a number in parentheses, or it could be plus a number. So this is kind of counterintuitive a little bit because a negative number in the parentheses actually moves it in the positive direction horizontally. So this would actually move it to the right c number of units. So if it was like x minus 4 in parentheses, it would shift it to the right 4 spaces. And then if you had f of x plus c in parentheses, the plus actually moves it in the negative direction horizontally. So it would move it to the left, that number of spaces right here. So what does that look like? Well, let's say we had the function h of x. And then if we had h of x minus 4, where x minus 4 is in parentheses, it shifts the graph over 4 spaces to the right. So it comes over here. And if we had h of x plus 3 in parentheses, then the plus 3 shifts it in the negative direction 3 spaces. So it'd be 3 spaces to the left, which gives you this graph right here. So let's try some examples with graphing using vertical and horizontal shifts. Here we have a curve. All right, this is our function f of x. And let's say we had, we're trying to graph f of x minus 3 and then plus 5. Well, in this case, okay, the minus 3 is going to shift everything to the right 3. So it's going to be shifting to the right 3. And the plus 5 outside of the parentheses is our vertical shift. It's shifting the graph up 5 spaces. So we shift the graph up 5 spaces and then to the right 3 spaces. And now we have our new curve right here. All right, so our graph can be shifted both horizontally and vertically at the same time with these different numbers. Now another concept with graphing is reflections. So a reflection creates a mirror image of something. So here, for example, we have y equals negative f of x. And what that does is it reflects the f of x function across the x-axis. Because we're taking whatever y value we had and changing the sign. All right, so for example, if we had f of x right here, okay, negative f of x would reflect this function across the x-axis. So how does that work exactly? Well, let's say we picked a point. Let's pick the vertex first right here. So let's say the vertex is at the point maybe 0, 3. Okay, just making up a number. Okay, so to reflect it across the x-axis, you're going to change the sign of your y value. So instead of positive 3, we're going to put negative 3. So this point here is going to be instead at 0, negative 3. And that goes for any point. We just pick any point on the original graph. Let's say this was negative 2, 7. Then our other point, to reflect it across the x-axis, we change the sign of the y value. So now we have negative 2, negative 7, which takes you right here. So if you were told to reflect a function across the x-axis, you would do it in that manner. You would basically pick a point on the graph and then reflect it across by changing the y value. Now the same concept is true for reflection across the y-axis. To reflect a function across the y-axis, you change the sign of the x value. So if you had this function g of x right here, then negative g of x would be reflected across the y-axis like this. So typically you'd pick like the beginning and ending point. So if you had this point right here, let's call that 2, 0. You have to change the x value, change the sign, so you get negative 2, 0. And that would take you to this point right here. And then you would take this other point on g of x, take this other endpoint, we'll call that maybe 7, 3. Then you change the x value, change the sign to be negative 7, 3. And that would take you to this point right here. So once you have those 2 points, you can create a curve, and that would be the reflection of your original graph. So let's try an example of graphing by using reflections. Here we have f of x, and we're trying to use f of x to sketch the graph of g of x equals negative f of x, and h of x equals f of negative x. All right, so we're doing two things. We are graphing negative f of x, and we're graphing f of negative x. So the negative f of x, this is the one where f of x is your y value, right? So negative y means we're switching the y value. So if it's positive, make it negative. So if you switch the y value like that, that's going to be reflecting it across the x-axis. So if you find this point here, this point is at 1, 2. Okay, you change the y value to be now 1, negative 2. That gives you this point right here. And then you take this other endpoint. That would be, what, 1, 2, 3, 4, 5, 6, maybe 7-ish. So somewhere around 7, up 1, 2, 3, 4, 7, 4, right about. That's 7, 4. So you change the y value, and that would give you 7, negative 4. So it'd be over 7, and then down 4. 1, 2, 3, 4, right here. All right, and you connect the dots with the curve, and you're going to get this graph. And I guess that was supposed to be about 5, maybe 7, 5. All right, so go down here at 5. So it's not totally exact with the picture, but we get the idea, hopefully. Where you just change the y value from positive to negative. And now to find f of negative x, what we're doing is we're changing our x value and making it the opposite sign. So here again, if this was our point of 1, 2, you change the x value to be negative 1. So you have negative 1, 2, and that takes you right here. And then this point, if we said that was maybe at 7, 5, I think is what it looked like it was, 7, 5, you change the x value to be negative 7, 5. So 1, 2, 3, 4, 5, 6, 7, and then up 5. That would take you right around here. All right, then you connect the dots, and we're going to get this new curve. So we're off just by a little bit, but you get this new curve right here. All right, so that's the idea with this. You can reflect across the x and the y-axis in that manner. Now another thing with graphs is we can compress or stretch a graph or a function. So we have vertical stretching and compressing, and we also have horizontal stretching and compressing. So for vertical stretching or compressing, what we're doing is we take the function and multiply it by some number. So if that number is bigger than 1, that's going to stretch it out vertically. So it's going to make it go up higher and down lower. All right, and then if the number that you're multiplying by is a fraction, something between 0 and 1, then that's going to compress the graph vertically, making it not go as high or as low. All right, so for example, if we had this function f of x, and let's say we were to do 2 times f of x. Okay, because 2 is bigger than 1, okay, it's going to compress it vertically. So what you do basically is pick any point that we started with. So you pick a point, whatever that y value is, you multiply it by 2 to get your new point. So if this were at, let's say, negative 1, 2, multiply the y value of 2 by 2, that would give you negative 1, 4. So take it up here instead. All right, and then same thing for 1, positive 1, 2. Multiply 2 by 2 to get your new y value of 4. And if it was like negative 2, 6 maybe, or a negative 2, 3, whatever the y value is, multiply it by 2. So when you do that, you're going to get a graph that looks like this. It makes it compress vertically. Now if you had 1/2 times f of x, okay, you take whatever point is on the original graph and take the y value and multiply it by 1/2. So if this green point here, we're at negative 1, 2, you multiply 2 by 1/2 to get negative 1, 1. So you get a point that's halfway between the original point and that x-axis. So when you do that, you're going to get a graph that looks something like this here in green. So we have that, and we also have horizontal stretching and compressing. So the way this happens is by multiplying the number, the f of x, multiplying the x in the parentheses by a constant. All right, and so if you multiply by a number bigger than 1, you're compressing the function. And if you're multiplying by a number less than 1, so I guess a fraction between 0 and 1, it's going to stretch out horizontally the function. And the amount by which it's being stretched or compressed is you take the constant that you're multiplying by and take the reciprocal of that. And that's going to be the factor by which you're compressing or stretching. So for example, if you had this graph of g of x, and you were told to graph g of 2x. So because 2 is bigger than 1, okay, it's going to compress the graph. It's going to make it squish together. And it's going to do that by a factor of 1 over c, or 1 over 2 in this case. So whatever x value you had, let's say this x value were, let's say, a 4, okay, you have to take half of that. That's the factor here that you're compressing by. Half of 4 is 2, so it's going to go right here. So that point is being squished over here. Same thing for this point. You know, squish it in by half right here. And that's going to give you your new point. So if you do that, you're going to get a graph that looks something like this, where the graph is now squished together. And then if you had g of 1/2 x, g of 1/2 x. So 1/2 is between 0 and 1, so it's going to stretch out the graph. All right, and it's going to do that by a factor of the reciprocal of 1 over 2, which would be 2 over 1 or 2. So we're going to take any x value on the original graph and multiply the x value by 2 to get the new x value of your point. So if this point here we're at, let's say 2, 0, then you have to multiply by 2 to get your new point, which is going to be 4, 0. Same thing here. If this point were negative 2, 0, multiply negative 2 by 2 to get negative 4, 0. And then we can connect those new dots that we have. We're going to get a graph that looks something like this. All right, so make sure you know how to use the constant being multiplied to compress or stretch the graph as needed. So here's one more example where we are given a function, and now we're trying to find 2 times f of x and f times 2 of x. All right, so this will give you some practice with the compression and stretching, and this is going to be with a different type of graph. So we've already kind of did the f of 2x, we've already kind of done that, but we've not done 2 times f of x with this type of graph. So beginning here, trying to find 2 times f of x. The 2 is being multiplied by f of x, which means it's 2 times your y value. So what you're going to do is you find your points. So let's say here, this point. Okay, this point is over at, the y value is 1, 2, 3. So you're multiplying that y value by 2 because of the 2 in the front. That's going to take you up to 6. So 4, 5, 6, way up here. So that point is now going to be way up here. All right, your y values that are at 0 are going to stay where they're at. So you get that point here, this point here, this point here would all stay where they're at. And then this point here at the end, that was at 1, 2, 3, negative 3. So multiply that by 2. That would take you down to negative 6, which is down here. All right, and same thing with this point. It's going to come down to here. And then this point is going to go up to here with the other one. So we can connect the dots. So the dots of the new graph, it's going to go something like this. All right, so this would be your new graph. So that would be for g of x. That would be your 2 times f of x. And now for the other one, for f of 2x, we take our x values and multiply by 2. Actually, not by 2, by 1/2. So the 2, you have to take the reciprocal. So c, your factor is going to be by 1/2. So any x value that we have, so like right here, for example, okay, it's going to be compressed by half. So that x value was what? 1, 2, 3, negative 3. It's now going to become negative 1.5 right here. And then this x value of 0 is going to stay where it's at. This value of 3 for x is going to go over here to 1.5. And the amplitude, or the height, is going to stay the same. So it's going to look something like this. All right, so it's going to look something like this. So the height and the depth is going to stay the same. All right, we could keep that going if we wanted to, but this would be kind of your general shape. All right, so that's going to be the graph of f of 2 of x. So in this lesson, we learned all about the different graphs of functions and how the different numbers can affect the graph as well. And that concludes our lesson for today. We will see you next time.